Okay, we are discussing about the band gap engineering. Basically, as we have discussed earlier, that if you want to tune the band gap of a material for a particular application or for a application which is suitable for some device etc., then we have no other option but to go for the band gap engineering, because you know that nature does not support any kind of material having any kind of band gap. So, there are certain materials or elements or compounds which have certain band gaps, but those will not be useful for all the applications. So, that is the reason that band gap engineering are resorted to, and in that band gap engineering basically we use some epitaxial machines. Okay, epitaxy means single crystal thin film, and thin means it is really thin, it is very thin, of the order of some angstrom, and for which you need a suitable substrate having a lattice constant equal to the lattice constant of the grown layer. So, as discussed earlier that there are different techniques for epitaxial growth. One is say liquid phase epitaxy, which is known as the LPE. Another is say vapor phase epitaxy. Number 3 is MBE, molecular beam epitaxy. Now, apart from this all epitaxial techniques, there are other epitaxial techniques as well, and today we shall discuss about the liquid phase epitaxy. Then if you see in this slide that liquid phase epitaxy basically an epitaxy which is known as the growth from the melt or solution. Remember that it is a growth from the melt or solution. Unlike other epitaxial techniques where we will find that no melt or solution is used, okay, either vapor is used or molecular beam is used, but only LP is the only technique where we will use the melt or solution. And in this epitaxial technique, you see that single crystal epitaxial layer is grown on a parent substrate from the precipitation of a crystallized phase from a saturated solution of the constituents. That is very important thing, this term, that the saturated solution of the constituents. Now, what is saturated solution? Basically, the principle of growth of LP is that a mixture of the semiconductor with one of its constituent elements melts at a much lower temperature than the semiconductor itself. This is the principle. That means, if you take the example of gallium arsenide, its melting point is how much? 1240 degree centigrade, say exclusively it is precisely it is 1237 degree centigrade. Now, if you want to melt gallium arsenide, how much temperature is required? 1240 degree centigrade. But if you add certain amount of gallium or indium with gallium arsenide, then the melting point will come down to 800 or 900 degree centigrade. So, that is the principle of growth for this LPE technique. A mixture of the semiconductor with one of its constituent elements melts at a much lower temperature than the semiconductor itself. Much lower temperature means it is say 800 or 900 or 700 degree centigrade. So, that is the principle of growth for LPE. Then as usual that you need a substrate on which the crystalline phase will be precipitated, and the crystallographic orientation of the grown layer is determined by that of the substrate. Obviously, here you know that in epitaxial technique the substrate plays the role of the seed crystal in bulk crystal growth. In bulk crystal growth, what we found? You need a seed. Okay? The seed is placed on the melt and then slowly pulled. That was the bulk crystal growth technique. That seed basically gives you the orientation of the grown crystal from the melt. That means, the crystal from the melt will assume the orientation of the seed crystal. If the seed crystal is 100, then the whole crystal will be 100. Similarly, in epitaxial growth technique, remember that we do not use any seed crystal. Here the seed crystal basically the substrate. substrate plays the role of the seed. So, if the substrate is 100, then the epitaxial layer will be 100. If the substrate is 111, the epitaxial crystal will also be 111. So, substrate is equivalent to seed in epitaxial growth technique. Another thing is that we have seen that for bulk crystal growth using seed, the melt is kept in a crucible. Okay? The melt is kept in a crucible. Here the melt will be placed not in a crucible, but some other container is there, as we shall show you. And one of the problem of LP is that the ultra thin layers cannot be realized. That is the problem of the LP crystal growth. So, we shall discuss this thing in detail. Okay, now, as mentioned earlier, if a solution of mixture of gallium arsenide and gallium is formed, remember that we would like to make a solution. Solution of what? Solution of gallium arsenide and gallium. Now, what is the melting point of gallium?
20 or 20.
No, it is almost 38 exactly, because it is liquid at room temperature almost. So, its melting point is very low. So, if you put gallium and gallium arsenide, then it will be a solution, and then it is possible to recrystallize gallium arsenide from the solution by cooling it at temperatures from 600 degrees centigrade to 800 degrees centigrade. That means, the growth temperature will be between 6 to 800 degrees centigrade. What was the temperature required for the Chouralski or Bridgman technique for gallium arsenide? It is the melting point of gallium arsenide, 1240 degrees centigrade. Here you see that it is almost half, 600 to 800 degrees centigrade, depending on the growth apparatus, growth machine, etc. You need temperature from 600 to 800 degrees centigrade, and which is much lower than the melting temperature of gallium arsenide, which is 1237 degrees centigrade. And LP growth occurs from a solution at a temperature well below the melting point of the semiconductor, as it is discussed, and that is why it is known as the growth from the melt or solution. Unlike in other epitaxial techniques, where we find that either the vapor or the molecular state of the matter will be used for the deposition of the epitaxial layer on the substrate. So, usually molten gallium or indium, you can use indium as well. We have given you the example of gallium plus gallium arsenide, but you can use indium plus gallium arsenide as well. Then also the temperature will be low, but not as low as what we find for gallium plus gallium arsenide, because the melting point of gallium is too low, because it is almost liquid at room temperature. Usually molten gallium or indium are used to form the melt, and so LPE is commonly described as solution or melt growth. So, the whole idea is that you take gallium arsenide semiconductor and you mix gallium with it, make a saturated solution of gallium arsenide and gallium, or gallium arsenide plus arsenic. You can for indium phosphide plus indium, right. So, generally gallium arsenide or indium phosphide are grown from by the epitaxial technique. So, either we use gallium or indium, because if you can ask me, sir, why arsenic is not used. Arsenic can be used theoretically, but problem is again the vapor pressure of arsenic. Problem is again the vapor pressure of arsenic. Say if you choose the region of 800 to 600 degrees centigrade, from 600 to 800 degrees centigrade, that there will be loss of arsenic as well, because you have seen that for Bridgman growth what we did, basically we put some arsenic at one end of the boat, right, so that any loss due to the decomposition from the surface can be compensated by the arsenic which was placed in the reserve. Basically, you can think that there was an arsenic reservoir, or in case of Choudalsky technique we used B2O3, okay, encapsulated. Yes, we have covered the molten surface by B2O3. So, that is why generally arsenic or phosphorus are not used, they are not favorable. Okay. Generally gallium or indium is used. But this growth actually is a thermodynamic equilibrium growth. So, you have to use the phase diagram. This is a phase diagram of gallium and arsenic. Basically, it is applicable for any binary compounds, 3,5 binary compounds, right. So, suppose you have a semiconductor AC, say A is gallium, C is arsenic, or A is indium, C is phosphorus. So, when you put gallium with gallium arsenide, or say you put A with AC, basically A is say gallium, AC is gallium arsenide. So, if you mix A with AC, generally the liquid will contain molecules of gallium arsenide as well as gallium and arsenic as atom, right, because for equilibrium it is very much necessary that AC must be A plus C. Okay. So, that means the liquid will contain the molecule of AC as well as the atoms of A and C. So, that when you mix with A, it will be a liquid containing both AC and A and C, and as soon as it will get a substrate for recrystallization, when the temperature is lowered, A and C atoms will be absorbed by the substrate surface and AC film will be grown. So, that is why it is known as the thermodynamic equilibrium growth, and all such thermodynamic equilibrium growth will be governed by the phase diagram. Now, if you consider this phase diagram, what you see? You see that there is a curved line which is known as the liquidus. What is liquidus? That means above this line it is liquid, above this line it is liquid. So, that means you see what we have plotted in the phase diagram, we have plotted the temperature. Here in the y axis you see the temperature is from 29.5 to 1400 degrees centigrade, okay. And in the x axis the atomic percent of arsenic. Atomic percent of arsenic means when I come to this point at 0, that means there is no arsenic at all, it is fully gallium. Similarly, when you come to this point at 100 arsenic concentration, that means there is no gallium, and at 50 you see that gallium arsenide with stoichiometry will be grown. With stoichiometry you can grow here also, then that will be non stoichiometry. That means if you grow here, you find that it is less than 50 arsenic, that means it will be gallium rich. So, you take this gallium rich here, you see that I have mentioned gallium arsenide plus gallium, because this is the gallium rich, and on the right hand side of this 50% atomic percent arsenic means it is gallium arsenide plus arsenic, plus in this region there will be more arsenic, in this region there will be more gallium, right. So, you find that at 50% atomic concentration of arsenic. Here it is solidus, that means it will be a solid. So, if you melt gallium arsenide and if you go for the bulk crystallization, you find that, say let us take an example of say X. What is X? X is 85% arsenic. So, this point means T1 the temperature and X is 85% arsenic. So, under such a circumstance, if you reduce the temperature from say T1 to this line, that means what will happen? This liquid will be solidified as the temperature is reduced, right. Similarly, you see that in LP, that is for the bulk crystal growth, but for LP we need liquid. So, liquid means you see that the left portion of this phase diagram can be used. Say this is temperature TA, you see this point is temperature TA, and what is the state of gallium arsenide in this region? It is obviously liquid, because this is the liquidus curve. So, all such portions will be liquid. So, as you lower the temperature from TA to TB, okay, TA say 850 and TB say 650, or say from 800 to 600, any two temperature. If you reduce temperature from TA to TB, it will solidify. It will solidify. So, the temperature, how you will choose the temperature, how you will choose the composition, that will be fully governed by the phase diagram. For any crystal growth, you need a phase diagram, and phase diagram is available in the literature, because people have been growing gallium arsenide for many years. So, there is no dearth of data in the data bank, right. You have many data on gallium arsenide, indium phosphide. So, you can take this phase diagram, and depending on your system, whether you want to make the bulk crystal growth or the liquid crystal growth, whatever be the case, you choose the temperature or that region. But what will happen in this region? You see that since it is rich in gallium, so what will happen? There may be some non stoichiometry, but the composition will be like this. Say gallium 0.0051 and arsenic say 0.0049 type of thing, right. So, that means for all practical purpose, that is a stoichiometry growth for all practical purpose. Minutely, if you make the chemical analysis of the growth epitaxial layer, you will find that there may be some deficiency of arsenic or that, but that is in practical it is as good as a stoichiometric layer, because you see that in this case it comes at the 4th place of decimal, it comes at the 4th place of decimal. So, you see that the phase diagram is an important thing, and it is a growth from the melt or solution. That means, the left part of the phase diagram we shall use. Here I have shown that gallium and gallium arsenide is mixed. So, it becomes liquid gallium arsenide. That means, in the liquid there will be gallium arsenide as well as the atoms of gallium and arsenic, and if you reduce the temperature from this part to that part, that means it will solidify, and then you can say that it is the epitaxial growth of the gallium arsenide. Yes, if you have any question.
In this left part, sir, the liquidus curve is touches 400 degrees centigrade.
Yes.
So, at this point, means if we go to 400 to 600, 800, means liquid portion is available. Means melting of gallium arsenide starts at 400 degrees centigrade.
Not melting, basically as you mixed gallium, so it becomes a solution. Problem is not 400 or 600 degree centigrade. Why? the lower limit of the temperature will be determined by the fact that there will be surface absorption. Okay, there will be surface absorption. So, what is the substrate? Substrate is gallium arsenide. What is the deposition? Gallium arsenide. So, that means on the substrate surface there will be absorption of gallium and arsenic atoms. For that one minimum temperature is required. So, you cannot go beyond that temperature. Maybe that at 400 that is not possible. Some more temperature is required, say that absorption is possible at 600 degree centigrade. So, even if the temperature is 400 degree centigrade, you cannot use that temperature. For a particular material, it has a surface absorption temperature, below which it will not be absorbed on the surface, and so the growth will not take place. Okay. So, you have to come from say Ta to Tb, that is arbitrary, say from 800 to 600, then you have to cool below 600, because in 600 also, as you told, it will be in the molten state. On 600 it will be on the molten state. So, that it will, the system will be cooled down, only then it will be a solid epitaxial layer. Yeah, what we have discussed, I have written here, the melt consisting of component A saturated with component C by dissolution at temperature Tb is brought in contact with the substrate and the temperature is gradually ramped down. The solid Ac leaves the solution and recrystallizes on the substrate. As the cooling continues, the epitaxial crystal continues to grow. The rate of cooling decides the growth rate, and the epitaxial layer thickness is determined by the total duration during which the melt is cooled and held on the substrate. So, cooling rate is basically the growth rate. Okay, the growth rate will be determined by the cooling rate. Cooling rate means, say in this case, if you say that the temperature is lowered from Tb to Ta in say 1 hour. So, what is the rate of cooling? Tb minus Ta degree centigrade per hour. If it is 800, if it is 600, that cooling rate is 200 degree centigrade per hour. So, you can change that cooling rate by means of a computer control system. All such crystal growth systems have computer interface. Very good control can be made using some computer or microcontroller system. So, you can make some programming, what cooling rate you want. If you want that the cooling rate will be 1 degree centigrade per hour, that can be made. So, the temperature controller will have to be programmed in such a fashion that the cooling rate will be 1 degree centigrade per hour. So, depending on your cooling rate or the growth rate, suppose you want a growth rate of say 100 angstrom per second, that means 10 nanometer per second, or say 100 angstrom per minute or 100 angstrom per hour. So, depending on your growth rate, you have to fix your cooling rate. And if your growth rate is say 100 angstrom per second, that means if you grow for 60 seconds, what should be the thickness? 6000 angstrom. If you grow for the 100 second, what should be the thickness? 10,000 angstrom. So, depending on your growth rate, you can calculate how much time is required for the growth to complete for a particular thickness. Suppose for a particular application you need 1 micron thickness, and the growth rate is say 10 angstrom per second. So, what should be the time? If 1 micron thickness is required for a particular application and if the growth rate is 10 angstrom per second, then what should be the time? Time is 1 micron divided by 10 angstrom. 1 micron divided by 10 angstrom, that much second. If you divide by 60, that much minute, again further 60 you will get hour. So, you can fix the temperature of growth for how long you will make the growth depending on the thickness. Now, how the thickness is measured? How you can calculate the growth rate? How you can calculate the growth rate experimentally? I would like to know the experimental technique using which you can know the growth rate of a particular technique. No. Can XRD measure the thickness? There are many techniques. One important technique that you all know, it can be done by transmission electron microscopy. Why? Because substrate and thickness, they are different. Okay, substrate and thickness, they are different. So, using a transmission electron microscopy, you can view the growth actually. That means, if it is your substrate and say it is your epitaxial growth layer, using a high resolution TM, HRTM, you can see this picture and you can measure this thickness using the scale. Okay. Another thing is that there is a stylus measurement, STYLUS, stylus. Stylus basically it is related to the refractive index. So, variation of the refractive index you can measure the growth rate. Suppose you want to make the note the growth rate of gallium arsenide, then what you have to do? You have to take a say sapphire or silicon substrate and you grow gallium arsenide. Refractive index of gallium arsenide is different from that of silicon. So, from the refractive index variation, the thickness can be calculated. That is very simple thing. Stylus, STYLUS, thickness measurement unit. Right. So, you can measure the thickness of the grown layer, and suppose you have grown for 1 hour and you find the thickness is 1 micron, then what is the growth rate? 1 micron per hour. So, you can convert it into second or minute. So, you will be knowing what is the growth rate for your particular system. And remember that growth rate of gallium arsenide is not same as the growth rate of indium phosphide or the growth rate of silicon. It is completely different because the thermodynamics is different. One example I can give you that for gallium arsenide and indium phosphide, the growth rate is low in gallium arsenide. Why? Because the cracking efficiency of arsenic is less than that of phosphorus. The cracking efficiency of arsenic is less than that of phosphorus. So, if you grow gallium arsenide, the growth rate will be lower than indium phosphide, because unless it cracks, it will not be absorbed on the surface, and so the growth will not take place. Okay. So, that is the reason that not necessarily that all growth will be of the same type of rate. Okay. LP, so far as the LP apparatus is concerned, it is very simple. That is the beauty of LP. If you compare LP with other system, say vapor phase epitaxy or MB or MOCVD, MOVP, whatever be the other techniques, all other techniques are very, so far as the apparatus is concerned, it is very complex type of system. It is very complex type of system. Here in LP's apparatus you see that it consists of a graphite slider and boat assembly inside a quartz furnace tube with accurate temperature control. That means, you have to make a quartz furnace tube. On that quartz furnace tube you must have a graphite slider and boat. Slider means this is slider, it you can slide, basically you can slide, okay. It is like dryer, say, and this is the boat, and on the boat there are groups or bins. Say here I have shown you melt 1, melt 2, melt 3, forget about melt 2, melt 3. Let us take a concrete example that melt 1 is there. What is melt 1? In melt 1 there will be gallium arsenide plus gallium at a particular temperature, say 800 degree centigrade. Then you put a substrate with its say clean surface on the top, because you have to grow the epitaxial layer on the substrate. So, our aim is to put the substrate just below the melt, which can be done by the slider. So, first if you pull the slider, what will happen? The substrate will come in touch with melt 1, then you reduce the temperature and say you have calculated that half an hour is required for 1 micron growth, you need 1 micron growth. So, you stay here for half an hour, okay. You stay here for half an hour, then you pull it, remove it, then you totally cool down the system, okay. So, that means it consists of a graphite slider and boat assembly inside a quartz furnace tube with accurate temperature control. The melt is held in a groove or bin in the boat. That means, groove or bin means this is groove or bin where the melt is kept. So, here we do not use crucible type of thing. The substrate is held with the growth surface pointing upward in an opening slider, in an opening in a slider with the growth surface pointing upward. That means, suppose this is your substrate, and you know that on the substrate there are two faces. Generally on one face the growth is made. Why? Because on the both the sides you cannot make the growth, you have to put the substrate on some platform. So, that is why you will find that on one side where there is a rough side, not the two sides are polished, one side will be polished surface, another will be unpolished surface. Because when from the bulk crystal the substrate is made, that means it is cut into pieces, one side is generally polished, because polishing also needs cost. So, if you want both sides polished, that is also available in the market, then the cost will be simply double. If one piece of gallium arsenide with one side polished costs rupees 20,000, 2 inch, I am talking about 2 inch substrate, 2 inch gallium arsenide substrate, one side polished, it costs more than 20,000 rupees in Indian market. If you want that both sides are polished, then it will be 35,000-40,000 rupees. So, one side polish, on the polished surface you have to make the growth, and as usual that the polished surface have to clean, because there may be some oxide formation, and because of your handling that the fingerprints can be on the substrate surface. That means, you need degreasing. One point is degreasing. And number 2 is the removal of impurities or contaminations. Okay. Degreasing means grease, grease means oily substance, grease means oily substance, you have to remove the oily substance. How the oily substance are removed? Can you tell? What is the technique using which the oily substances are removed? You all know. Here you cannot use soap. Basically, you have to use some organic solvent. Yes, yes. Generally, for 3,5 semiconductor substrates, the gallium arsenide or indium phosphide, first it is boiled in trichloroethylene TCE. Okay. First you boil in trichloroethylene. You take a beaker, you put some trichloroethylene, say 5 cc, 10 cc, put your substrate. Generally, on in our laboratory level growth, the substrate is 1 centimeter by 1 centimeter. We do not use the whole 2 inch wafer. Okay. For lab scale, you use 1 centimeter by 1 centimeter or 1 inch by 1 inch substrate. That means, we have to cut a piece from that 2 inch diameter substrate. Then you take a beaker, put some TCE, put the substrate on TCE inside the beaker and place it in a heater. For 5 minutes you boil it. Okay. So, what will happen? Yes, actually the oily substances will be dissolved by TCE, but TCE means it has carbon. So, now if you put your substrate in the growth apparatus, then what will happen? Carbon contamination will be there, because on the surface there will be carbons. Then you have to remove TCE. How to remove TCE? No, TCE is removed by acetone. There is a step. Then you remove TCE from the beaker and you put acetone, you rinse with acetone. So, the job of the acetone is to remove trichloroethylene. Acetone has also carbon component. Okay. Acetone has also carbon component. Then what will happen? You have to remove acetone by methanol. Remove acetone by methanol. Okay. Then you have to remove methanol, because methanol has also carbon, deionized water. Yes. Then you rinse your substrate by DI water, deionized water, DI water.
So I have to boil, yeah, I put it in ultrasonic cleaner.
No, you have to boil it. Okay. So, these are the steps normally we use for degreasing a substrate. It is always done.
Sir, acetone can dissolve oil?
Yes, acetone can dissolve oil, but TCE can dissolve in a better way, much better way. So, people have basically standardized such kind of cleaning process. Okay. These are basically invented in the Bell Lab, because they are the main what I should say, that all such discoveries or invention were from the Bell Labs, so far as these electronic materials and the microelectronics is concerned. So, they have standardized this method and we follow their standard methods only. Okay. Maybe there are other substances, not that these are the only process, there are several processes as well, but people have taken as a standard thing because the Bell Lab use it. Probably that what you told, that acetone, if you boil the substrate with acetone, the same result can be there, I admit. But since we follow those process, so we have taken as a standard. First boil in acid TCE, then you remove TCE by acetone, then you remove acetone by methanol, and methanol can easily be removed by DI water. But you cannot remove TCE or acetone by DI water, there will be carbon signature in it. And another thing is that in some cases that you have opened the packet, you have opened the packet for in which the wafer was kept. Okay. First the wafer, when it is imported, it is put inside a airtight cover packet. So, you cut the packet, remove the wafer. As soon as you remove it, it come in contact with the atmosphere, it immediately gets oxidized, particularly the silicon. Gallium arsenide indium phosphide also oxidized, but not as easily like silicon. Then what you have made one piece, say 2 inch by 2 inch or 1 inch by 1 inch. Then so what about the other pieces? They will be fully oxidized. So, on second day, when you want to make some growth using another piece, you have to remove the oxide layer from the substrate. For oxide layer removal, there are several techniques. Okay. Generally H2SO4, H2O2 and water is used. Etching, in my previous lecture I have given you the composition, generally H2SO4 or HNO3 along with hydrogen peroxide H2O2 and water is used. And sometimes you find that HF is used to remove the oxide, particularly from silicon, HF is used. So, those are the techniques which one should follow religiously. Okay? One should follow religiously, otherwise what will happen? Between the substrate and the epitaxial layer, there will be a oxide layer. That oxide layer not only will reduce the efficiency of your device, but at the same time there will be lattice mismatch. Epitaxial layer of gallium arsenide is lattice matched to substrate gallium arsenide, not with gallium oxide, because the lattice constant of gallium oxide is different from that of the. Another thing is that gallium oxide or silicon dioxide, whatever be the oxide, they are basically insulator in nature. So, when you put current, what will happen? They will, the electrons movement will be restricted or it will be scattered, because that is an insulation. So, from the substrate to the epitaxial layer, there will be no current path. So, that is why you have to remove oxide. All the time you use either epi-ready substrate. One thing is that there is epi-ready substrate, epi-ready. Epi-ready means the substrate is ready for epitaxial growth. Okay? The substrate is ready for epitaxial growth, that is known as the epi-ready. That means, when you would like to grow on 2 inch, 3 inch or 5 inch diameter whole crystal, whole wafer, then you just cut the packet, take the wafer and put it inside the epitaxial machine. You need not to make any treatment, when the whole wafer is used as a substrate. In generally for microelectronics fabrication or IC fabrication, the whole wafer is used, but in lab scale it is 1 centimeter by 1 centimeter or 1 inch by 1 inch type of thing. So, for lab scale religiously we have to follow the oxide removal as well as the degreasing steps, but if you can use epi-ready substrate, then you need not to follow those things. Okay. So, here we were that the substrate is held with the growth surface pointing upward. Growth surface means the polished surface. Growth surface means the polished surface on which the growth takes place in an opening in a slider. The slider can move along a groove cut along the length of the boat. So, this is your substrate, the polished face is facing upward and you can make the movement by moving the slider to and fro. So, that is the total setup. Here you see that there is a quartz furnace tube, and inside the furnace tube the whole thing is placed. Now, if you particularly take the example of gallium arsenide growth, you see that the saturated melt of gallium arsenide in gallium is held at the appropriate temperature. That means, in one of the bins, say in melt 1 you take gallium with gallium arsenide. The slider is moved so that the substrate is positioned on top of the melt and is in contact with it. Okay. So, between the melt and the substrate there should not be anything, the substrate must touch the melt. So, that means, the slider movement or the arrangement must be there, so that you can easily touch so that the substrate can easily touch the melt with its polished surface upward. The melt temperature is then lowered at a predetermined rate, during which the atoms from the melt crystallize on the substrate surface to form the epitaxial layers. After the required thickness is grown, the slider with the substrate is moved away from the melt and the whole system is cooled down, because say the temperature was from 800 degree centigrade to 600 degree centigrade, but at 600 degree centigrade it is typically hot. Okay. So, you have to cool down, and remember that when you cool down it must be in the in an inert atmosphere, otherwise at 600 degree centigrade in presence of oxygen, some oxygen will react with gallium arsenide surface and gallium oxide or arsenic oxide can be formed. So, all such cool down etcetera must be in an inert atmosphere. Now, if we take the example of growth of heterojunction. Now, what is heterojunction? What do you mean by heterojunction? Because till now we were in the epitaxial growth of a particular layer. So, it can be gallium arsenide, it can be silicon, it can be indium phosphide, but what is heterojunction?
The junction is formed by two dissimilar semiconductors.
Right. Heterojunction means a junction formed by two dissimilar semiconductors. Junction formed by two dissimilar semiconductor. Okay. Dissimilar means,
Band gap is different.
obviously dissimilar means band gap is different to different material. Okay. Silicon p-n junction, it is not a heterojunction, it is basically a homojunction. Why? You have used silicon material, one side of it can be doped with p and then n. That means, you take a silicon, first you make it a p type by putting boron in it, and then you dope with arsenic, so that a p-n junction silicon is made. That is not heterojunction. Heterojunction means it is completely two different entity. Say this is gallium arsenide material, aluminum gallium arsenide. So, it is a heterojunction of gallium arsenide and aluminum gallium arsenide. Remember that is a double heterojunction. Why? This is junction J1 say, and this is junction J2 say. Okay? So, that is why it is known as the double heterojunction. When we shall discuss about the laser and LED, okay, you will find that this kind of structure is required. Okay. here I have written that as is required in lasers, as is required in lasers. So, double heterojunction structure, or say you want to make a quantum well. A quantum well means the same structure where
gallium arsenide is quantum well.
yes, gallium arsenide is the well and the barriers are aluminum gallium arsenide. But the difference between heterojunction and quantum well is that in heterojunction you can take any thickness, there is no thickness restriction. That means gallium arsenide can be x angstrom, can be y angstrom, can be z angstrom, anything. Similarly, aluminum gallium arsenide can be A angstrom, B angstrom, C angstrom, anything. But here in quantum well, the well and barrier thickness must be calculated very precisely, otherwise you will not get the quantum effect. You will not get the quantum effect. So, generally in quantum well, this gallium arsenide, aluminum gallium arsenide will be very small, very small. Say gallium arsenide is say 40 angstrom, 80 angstrom, that level, very small. So, if you want to make the heterojunction growth, then you see that multiple bins are used. Why multiple bin? In one bin you have to keep gallium arsenide plus gallium. In second bin you have to place aluminum gallium arsenide melt. Okay. If you see this structure, say bin 1 is aluminum gallium arsenide, bin 2 is gallium arsenide, bin 3 is again aluminum gallium arsenide. So that the successive bins, using successive bins, first say melt 1 is say aluminum gallium arsenide. So, the substrate comes where the aluminum gallium arsenide is deposited. Then melt 2, it is a gallium arsenide.
In gallium arsenide, gallium is mixed with gallium arsenide.
Obviously,
Aluminum gallium arsenide.
generally aluminum gallium arsenide, in gallium arsenide plus gallium melt is there, along with there will be aluminum. Okay. And also remember that those will be governed by the phase diagram. You cannot take any amount, you cannot use any temperature, it must be governed by the phase diagram of aluminum gallium arsenide. So, melt 1 is say aluminum gallium arsenide, melt 2 is say gallium arsenide, and melt 3 is again aluminum gallium arsenide. So, heterojunction can be made. And to dope a particular layer to a desired level, a predetermined amount of the dopant species in elemental form is dissolved in appropriate melt. Say you want to make p type, then you use zinc, elemental zinc with high purity, 10 and 11 N purity you can use, or say for n type you can use tin, Sn, elemental form, because you have seen that the elemental form is required, no compound. Then what are the advantages of LPE? The advantages of LPE is that simplicity of equipment, very simple, general safety is there, no gas or that type of thing, expensive vacuum equipment not required, this is expensive, not 4. Okay. Expensive vacuum requirement not required, as I shall show you that for MBE very expensive equipment is required, and so far as the safety is concerned, vapor phase epitaxy or the metal organic vapor phase epitaxy is not safe. High deposition rate, good crystal quality, high degree of reproducibility, and thickness and composition control is possible due to computer controlled equipment. You want to make say 1.2 micron, 1.35 micron, 0.75 micron. So, that is possible. So, these are the advantages. These advantages make the LPE growth very attractive, but it has some disadvantages as well. Okay. So, what are the disadvantages? The disadvantages are ultra thin layers. Ultra thin means less than 1000 angstrom, that means 100 nanometer. Okay. What is ultra thin? It is less than 1000 angstrom, or hyper abrupt junctions. cannot be grown using LPE. But modern device needs ultra thin layer as well as hyper abrupt junctions. What do you mean by hyper abrupt junctions? Hyper abrupt junction means the junctions will be like this. Okay, junctions will be like this. That means, suppose this is P type and this is N type. So, changeover from P type to N type will be very sharp, not like this. Is it sharp? Here you see that the junction is not sharp, because the junction has taken that type of a thickness. The width of the junction is very high. Okay. So, for PN junction, hyper abrupt junction is required. Okay. So, that is very important, that using LPE you cannot make hyper abrupt junction. There will be a smearing, there will be an extended type of junction on both sides. That means, P will be here also, N will be here also, smearing of P and N regions, right. And ultra thin means you cannot grow quantum well or quantum dot using LPE. Ultra thin means that thing, that you cannot grow quantum well, quantum dot, quantum wire using LPE. So, these are the drawbacks for the LPE. However, it has very many advantages, and so it is very attractive for normal junction or normal material growth. Okay. So, thank you.